Alright guys, welcome to your College Board help video for derivative concepts and applications. And once again, I hope you guys don't sit down and watch this whole video, just fast forward to the ones that you guys need help with. Alright, so let's go ahead and do number 1 here. So on number 1, we're told that f is a function on the interval from 0 to 8, but this is not a graph of f, this is a graph of f prime. And what we've learned in class is that anytime a function is above the x-axis, like this one is all the way up to here, anytime it's above the x-axis, it's positive. And that would apply to this green interval here. And so that would be on the interval from 0 to 6 that f prime is above the x-axis, and therefore f prime is positive. Now, something else that we've learned in this class is that when f prime is positive, that means that f is decreasing. I'm sorry, f is increasing. So now, we don't know what f is starting at. It doesn't tell us. It doesn't give us an initial condition. But it doesn't really matter, because whatever value f is starting at, it's increasing the whole way from here to here. So it's getting bigger and bigger. So whatever f starts at, it increases until we get to 6. Now, at 6, something happens. After we get to 6, now my derivative is below the x-axis. Okay, and when f prime is below the x-axis, that means that f prime is negative. And if f prime is negative, that would mean that f is decreasing. So now if f is decreasing on this interval, that means it's getting smaller. It's going from it was going up before, but now it's going down. Now our question here is, at what value of x does the absolute minimum of f occur? Now, we've usually talked in this class about the candidates test whenever you're doing extrema. The problem with this, though, is that they don't give you any values of f. But we do know our starting time, we do know our ending time, and we also know our one critical value is 6, because that's where the derivative equals 0. But I don't know what f is. But I do know that whatever f starts at, it gets bigger until we get to 6. So whatever goes here is that question mark plus more. Okay? And then after that, it starts to decrease. So whatever was up on number 6, our starting point plus more, it loses a little bit after that. Okay? And so the question here is where's our smallest number at? Well, we know it can't be this one, because this is where we started. It can't be this one is what I'm saying. The reason for that is because whatever we started here, it just got bigger and bigger and bigger until we got to 6. So I know it can't be here. That's actually going to be a relative maximum of some kind. So that's not going to be it. So is it our starting point, or is it the ending point? Well, it depends, right? It depends on how much we added. Well, how much did we add? Well, does it look like it increased more, or does it look like it decreased more? Which one of these looks like more happened? Well, as you can see, it was increasing a heck of a lot more than it was decreasing, right? So even though we added a whole bunch here to this, right? We added a whole bunch, but then we only subtracted a little bit away. So what do you think? Do you think that the biggest point would happen at 0 or at 8? Let's think about it. Let's just make up some numbers. Let's say 0 was, let's just say 0 was at 2, right? Well, after 6, I added a whole bunch to it. Let's just say I added 10 to it, and it became 12, because it increased a whole lot. But then at 8, it decreased, but it only decreased a little. So it didn't decrease anywhere near as much as it increased. And therefore, as you could see here, our minimum would happen right here at the beginning. Because even though we did decrease here, the amount that we decreased can't even begin to compare to the amount that we increased. And therefore, the starting point would have to be the absolute minimum. And so for this one, we would say the answer is A. All right, let's go ahead and move on to number 2. Okay, so this one's asking for an absolute max. So once again, we're going to be looking at our candidates test. And we're starting at -2 and ending at 4. And we want to find our critical values as well, which is where the derivative equals 0 or is undefined. The derivative would be 3x squared minus 6x. So now that's never going to be undefined because it's a polynomial, but it can equal 0. I'm going to set it equal to 0, and then I'm going to factor. And then we're going to set each piece equal to 0, and then we're going to solve. My guess is that this problem was probably intended to be a non-calculator question. Unfortunately, I don't see where it tells you guys whether or not you can use a calculator, so we'll just assume that you can use it whenever you want to, but I can tell that this one's pretty nicely set up for no calculator. I mean, it's pretty simple. You just go ahead and find the derivative and find those critical values. There's nothing in here that would require a calculator, really. I guess it makes it a little tedious when you actually got to go find all the values, though, because we do need to plug in each one of these numbers now. 0 is pretty easy to plug in. If you plug in 0 to your original function, you're just going to get 12. But let's go ahead and do the other numbers. I'm going to start by plugging in -2. That's going to give me -8 minus 12 plus 12, and that gives me -8. And you just kind of keep plugging all those in. I'll go ahead and do that real quick. And so these are the values I get. And now the question is, the absolute max, which is this number right here, occurs at what x value? That would be 4. So the answer is A, 4. All right, so let's go ahead and take a look at this. Now, some of you guys might be, after you watch some of these, you're probably thinking, Mr. Bailey, how the heck am I supposed to know that? Well, that's what hopefully our next month is all about, just kind of showing you guys all the different ways these questions, these things that we've learned about can be asked. And you just kind of have to start learning how to think a little bit outside of the box and using all the stuff that we have learned to figure out answers in new circumstances, okay? Because that's just kind of how the AP test works out. Some of them are pretty straightforward, like the last one, but this one's a little bit tricky. I had to think about this one myself a little bit, and I think the best way to think about this is to graph this. So basically, if I create a graph of big F, I have an x value of A, and I've got another x value of B, but both of them have the same y value of -2. Now f of x, this big F, is differentiable, so it's continuous. So that means somehow those two dots are connected. Now there's a lot of ways you can connect them. I mean, you could connect them like this. You can connect them like this. You can connect them any way you want to. There's actually an infinite number of ways to connect those functions together. So it's really up to you on how you connect them. Okay, so keep that in mind, so that there's more than one way for these things to be connected together. But at least we know that. We know that we have A, we have B, they have the same y value, and somehow they're connected. All right, now take a look at the questions. Most of them are asking about little f. Now little f is right here. Now if you guys remember the second fundamental theorem of calculus, the derivative of big F can be found simply by dropping this integral and putting the x inside here, and you get this. So notice they're asking about f of x. Well, that's where it comes from. It comes from the second fundamental theorem of calculus. In other words, little f is the derivative or the slope of big F. Now let's see if some of these things make sense. Let's start with this one, C. Little f of x is less than 0. That means the slope of this function is always negative. Is that true? Well, no, that's not always true, obviously, because look at my graph. Over here, it's positive slope. So that can't be true, because my graph shows that based on the way I drew it, this does not have to be true. How about another one? Is the slope always positive? No, because we've got a negative over here, so that's also gone. How about here? Is the slope 0? A 0 slope happens anytime you've got a flat tangent line. Well, that would happen up here, so that is possible. Now let me ask you guys, can you possibly find a way to connect those 2 points? I have to redraw it, I accidentally deleted the whole thing. But can you guys possibly find a way to connect these 2 points so that there's no 0 slope? I challenge you to try it. No matter what you do, you're going to have a zero slope somewhere. You know, an idea occurred to me. What if I did this? Aha, there's no zero slope here. It's got a cusp. Well, that's not possible, though. It has to be differentiable. So that's not an option. It has to be smooth. And if it's smooth, somewhere you're going to have a flat line. So there's our answer. Now here, we'll just look at the last one for the heck of it here. Now this one's not asking about little f. This is actually asking about big F. Is it true that big F is less than or equal to 0 for all values of x? In other words, is the y value always below the x-axis? Well, the way I drew it here it is, but you guys remember my original graph looked like this. So no, it doesn't always have to be below the x-axis. Because based on the information we gave, there's any number of ways that that could have been drawn. The only one that has to be true is this. They do ask these questions. These ones are my least favorite types of questions on the AP exam because they're really hard for me to teach you guys about. Because really, they're asking about what is something that has to be true, which means that, well, it could be true in some circumstances, but which ones are have to be true? It's like, well, then you really got to know how to think outside the box and look at a bunch of different scenarios. But there you have it. Go ahead and move on to number 4. All right. Reading the question, you can see basically they just want to know how many relative maxes and how many relative mins there are. We have a graph of f prime. Now, f has a relative max when f prime goes from positive to negative, right? Or in other words, since we're looking at a graph of f prime above the x-axis to below the x-axis. So let's take a look at our graph here. As I go along, where do I go from above to below? Well, right here it'd be 1. To the left I'm above, and then to the right I'm below. So that would have to be a relative max. I'm going to put an X there for max. And then f has relative mins when the opposite is true. That would mean it's going from below the x-axis to above the x-axis. And that happens in 2 other spots right here. Here we're going from below and then it crosses to above. Below to above. So there's 2 relative minimums. I'll label those with n's. And 1 relative max. So that would be this guy. Seems like there's a lot of A answers on this thing. All right. I don't know. Maybe yours are in a different order. I don't know. Let's go ahead and take a look at number 5. So what would be really helpful here is if you knew the graph. Aha! They've given us a calculator icon. You know what that means? That means we're allowed to use our graphing calculator. So you could graph this. And graphing it will make it really simple to see. First of all, but a lot of you guys probably already knew what that looks like. It just looks like a V shape like this. So is it continuous? Well, there are no values of x that you're not allowed to plug in here. So yeah, it's continuous. I'm going to label that with a T for true. Is it differentiable at 0? No, that's a cusp. Can't have a cusp, so that's a false. Does it have an absolute minimum at 0? Yeah, it does. That's where the bottom of the graph is. So it would be really helpful if you knew what the graph looked like. So I see that numbers 1 and 3 are the answers. And so, hey, it's not A this time, it's D. Nice. This question is a little bit more standard, a little more up our alley. The question is asking for the average rate of change. The average rate of change can be found by doing f of b minus f of a over b minus a, where these numbers are a and are b. Okay, so if we just go ahead and plug those numbers in here to this formula, actually I shouldn't say f, we're using y, right? So I'll use y. Y of pi over 2 minus y of 0 over pi over 2 minus 0. So for the top, we have to plug these numbers into our function and see what we get. So let's start by plugging in the pi over 2. Now the 2's cancel. Notice this is a non-calculator question. So you kind of are at the mercy here of needing to know your trig, guys. And yeah, since it's a paper and pencil test, you're going to have to know this trig stuff. So If you haven't started already, which I've been telling you since the beginning of the year, by golly, make sure you start memorizing that unit circle and how to find these things. Cosine of pi is -1. All right, so this piece right up here on the top is -1. Pi over 2 minus 0, I'm just going to change that to pi over 2. And then we have y of 0. So that means I'm going to plug 0 in. 2 times 0 is 0, and cosine of 0 is 1. So I end up getting -1 minus 1 over pi over 2, which is -2 over pi over 2. Now you'll notice that none of those answers are an option over here. So I'm going to multiply the bottom by 2 to cancel out that fraction, but whatever you do to the bottom, you have to do the top. So I end up with -4 on the top and pi on the bottom. And that would be this guy right here. All right, go ahead and move on to number 7. All right, so number 7. Unfortunately, Cllgbrd does not do a very good job of making some of their questions legible. That was a problem for the past 2 years, actually. They're still working on it, I guess. But here we go. So we have a graph of y equals f of x. Okay, so this is a graph of f. And they're asking us on which interval is the derivative greater than 0 and the second derivative less than 0. All right. Well, if you guys understand that when the derivative is greater than 0, that means the original function is increasing. So when dy dx is greater than 0, that means f is increasing. And so long as you know that the second derivative being less than 0 means that it's concave down, that's what we're looking to find here. So on which of these intervals is f increasing and concave down? Now you got to be careful. When we did these questions in class, a lot of the times I was giving you the graph of f prime, but this is just a graph of f, okay? So this graph is increasing anytime it's going in an upward direction. So let me do a little color coding here. F is increasing anytime it's moving in an upward direction. So on this entire interval, it's increasing. And it's concave down anytime you have that bowl shape that looks like that. And so I would say probably from here to here. Now, on what interval are both of those things happening at the same time? Well, as you can see, it's here, from B to C. So there's only one place where those two things are happening simultaneously, and it's on the interval from B to C. So let's go ahead and take a look and see our choices here. So that would be option, it's kind of hard to see, but it looks like option B. All right, next question. All right, now I try not to pick too many of these types of questions. You guys see this little blue shield up here? That means that this is a secure question, and I'm not allowed to make a public video that goes over this. So I'm not going to be going over this particular question in the video. I can go over it in class with you guys, but I can't go over it on a YouTube video. So unfortunately, can't help you here with this one right now. We can talk about it in class. Hope I don't accidentally miss that one of these days and do it. Small little icon, I might miss it. But anyway, let's go ahead and move on to question number 9. All right, now this would be really awesome if I could just graph it, but I doubt many of you guys actually know how to graph this equation. In fact, I'm not too sure I know either, honestly. I'd have to think about it for a while. And it's not a calculator question, so we can't just look at the graph. But, okay, so they want to know which one of these statements is true. We'll look at all the questions. They're all about continuity and differentiability. So let's see. Is it continuous at x equals 2? Well, I don't know. Let's just try something really simple here. Let's try plugging it in. If you can't plug it in and get a real answer, then it's not continuous, right? It has to be defined. The absolute value of 2 is 2, and 2 take away 2 is 0, and the square root of 0 is 0. That's a real answer. It's a weird answer, but it's a real answer. So I'm going to say, yeah, it kind of looks like it's continuous. Why not? And if it's continuous, then the limit must be existing as well. But let's go ahead and keep going here. Is it differentiable at 2? Well, for that we're going to need to find the derivative. Now this is going to be a chain rule, okay? And you have to remember a couple of rules here. Let me review a couple of rules with you really quick. First of all, if you have a square root, and you want to find its derivative, then you basically just do 1 over 2 and put that square root in the bottom, and that's the derivative. Another kind of special square root we talked about was absolute values. If you want to take the derivative of an absolute value function, it's basically just going to be x over that absolute value. Okay, and so that's it. Pretty simple, right? Now, a lot of times you have to do a chain rule with these types. So like if there's something else in here, you have to multiply by the derivative of the inside. Same thing here. But that's the basic idea for finding derivatives of square roots and absolute values. All right, so I want to find the derivative of this function really quick. So the outermost function is the square root. So the way you find the derivative of square root is you do 1 over 2, and then you put the square root on the bottom, and that's it. Next, we're going to do the derivative of the inside of the square root, which is this. The 2 is just going to go away, but the derivative of the absolute value is going to be x over the absolute value of x. So I have to multiply by the derivative of the inside. It's a chain rule. All right, well, let's go ahead and plug in 2 to see if the derivative exists. We plugged in 2 to the original function to see if it's continuous. Oh, I didn't see it said not differentiable. We'll see. I know it's continuous. We'll say it's continuous. I don't know about this top one, actually, because I haven't checked differentiability yet. But that's what we're checking right now, so let's do it. Well, what happens if I plug in 2? Well, I end up with 1 over 0 times 1. And this is undefined. So the derivative doesn't exist at 2. So it's not differentiable, so we know it can't be b. This one says it's not differentiable, but it is continuous. This one's looking pretty good right now. So if I had to choose between A and C, I'm going to go with A because this one's just not specific enough. It is true that, oh wait, that one says f is not continuous. Gosh, I need to read these more carefully. It says f is not continuous. Well, we already said it is, so that's not true either. All right, so far we're looking pretty good here. F is continuous, but it's not differentiable. Nice. The next one here says the limit of f of x as x approaches 2 is not 0. Well, if the function's continuous at 2, then the limit has to exist and it has to be the same. So the definition of continuity technically is this. I'll put a 2 there for now. And we just found out that this thing equals 0. So if this function is continuous and f of 2 equals 0, then the limit has to equal 0. So this is also a false statement. Finally, x equals 2 is a vertical asymptote. Once again, if you have a vertical asymptote, that means it's not continuous. So this has to be the answer. It's continuous, but it's not differentiable. Why is it continuous? Because when I plugged in 2, I got an answer. Why is it not differentiable? Because when I found the derivative and plugged in 2, I didn't get an answer. And based on the fact that it was continuous, I could rule out these 3 things, and we have our answer there. So the answer is part A once again. All right, so question 10. So we have a table here. Notice that they want to know which one of these statements must be true. Well, they're giving me f double prime. Now, f double prime can only tell us things about f pertaining to points of inflection and concavity. Whenever we're talking about things like increasing, decreasing, or relative extrema, that has to do with the first derivative, not the second derivative. And so they didn't give us that information, so I'm going to rule those out right now. They didn't tell us anything about the first derivative, so I can't tell where it's increasing, decreasing, or where its relative extrema are. F double prime can tell us about points of inflection and concavity. Okay, so anytime the second derivative is positive, it's concave up. So like, for instance, here at x equals 0, since the second derivative is positive, my graph is concave up at that point. At x equals 2, since my graph has a negative second derivative, that means that my graph of f will be concave down. So as we go from 0 to 2, it looks like it changed concavity. So this statement seems to be true. The graph of f changes concavity somewhere on the interval from 0 to 2. Now, D, unfortunately, is a tricky one, but I know that this has to be true. I know that this one absolutely has to be true. Somewhere from here to here, we went from concave up to concave down. That has to be true. Did it happen right at 1? It looks like it probably did, because that's where the concavity is 0, and that's what we would call a point of inflection. So this one says, the graph of f has a point of inflection at 1. My only concern is that that might not be true necessarily. Maybe it's possible that the graph was concave up, and then it had a 0 concavity for a second, and then it kept going up a little bit, and then it started coming down somewhere else. And so maybe it's possible for there to just because a second derivative is 0, that does not mean you have a point of inflection necessarily. It has to change right at that point. And since there's some space between 0 and 1, it's possible that no change happened. Now, whenever we did these in class, I went ahead and said, okay, yeah, these are just probably going to be your points of inflection. Given the fact that they're giving us these two different answers, I know E has to be true, which means that since we're only allowed to pick one answer here, I'm going to go ahead and rule out D. And let's see if I'm right, because unlike you, I think I have the option to cheat and look. Yeah, so the answer is E. Tricky stuff. Unfortunately, I guess maybe I need to rethink how I teach this, because when I teach this with tables, anytime concavity goes from a positive to a negative, and there's a 0 there, I have always taught my students, okay, well, that's going to be a point of inflection. But I guess technically maybe not. Technically maybe not. So, all right, let's go ahead and move on to the next one there. So, little point to self there. Read all your options and go with the ones that are most certain. All right. Oh boy, we got another calculator-based question here. So you're allowed to use calculators on this one. All right, so the graph of f prime, the second derivative of f, is shown above. So this is a f double prime graph, okay? And let's review what we know about that right now. Anytime f double prime is above the x-axis, that means it's positive. And when f double prime is positive, that means that f is concave up. So let's write that down. So in this interval here, f would be concave up, and also on this interval here. Contrarily, on this interval and on this interval, f would be concave down because f double prime is below the x-axis, which means that f double prime is negative, which means that f is concave down. So the question here is saying, what are the intervals where the graph is concave down? Well, that'd be these orange ones. So from -2 up to -1, and then from 1 to 3 would be the answer. And so that would be option E there. So on this question, they're giving us a piecewise function, and they want to know, is it continuous at 3? Is it differentiable at 3? And does the limit exist at 3? Now, if it's continuous at 3, the limit has to exist, because that's part of the definition of continuity. So let's go ahead and begin. How can you tell if a piecewise function is continuous at that conjoining point, which is 3 in this case? Well, what you're going to do is we're going to find out what is f of 3. Then we're going to find what is the limit as x approaches 3 from the right. And then we're going to find what is the limit as x approaches 3 from the left. If all three of those come out to be the same value, then it's continuous. So let's do that. So first of all, f of 3. I want to plug 3 into this function. So where am I allowed to plug 3 in? Well, I'm allowed to plug in 3 anywhere where x equals 3. So right here is where x can equal 3, because it says it can be less than or equal to. So in this case, I'm going to use the x plus 2 equation. So I'm going to plug in x plus 2, and I'm plugging 3 in there for x. And for approaching 3 from the right, I'm looking for where x is greater than 3, so that would be this piece right here, the bottom one. So for that one, I'm going to plug in 3 as well. And then for where x is approaching 3 from the left, that's going to go back to the top where x is less than 3. So let's see if all three of these come out to be the same. This is 5, this is 5, and this is 5. They're all 5. And since they're all 5, it must be continuous. And if it's continuous, the limit has to exist also. The limit, now it's possible that the limit exists even though it's not continuous, but it's not possible for it to be continuous without the limit existing. If these two were the same but not this one, then that would mean that the limit exists even though it's not continuous. But since all three are equal, that means it's continuous and the limit exists. All right. So we already know that options 1 and 2 are possibilities. Now what about differentiability? Well, we just do the same thing we just did, but we do it with the derivative of this piecewise function. So to do that, we just take the derivative of the top, which is 1, and the derivative of the bottom, which is 4. So I'm not sure if we're allowed to plug in 3 yet, but let's just go ahead and go with it. When you take the derivative of a piecewise function, it's not necessarily true that you're allowed to plug in 3 because it's possible that it's not continuous. So, but we're going to go ahead and just go at it and see what happens here. So we need to approach 3 from the right of the derivative, and we need to approach 3 from the left of the derivative. Now, I'm going to wait on this because, like I say, it doesn't really matter. What really matters is this. Does the limit exist? Because if the limits exist, then this exists. That's just kind of how it works when you're doing derivatives of piecewise functions. So if I'm approaching 3 from the right, that would be the bottom. And in this case, that's this guy, where x is greater than 3. So I get 4 for a slope there. And if I'm approaching 3 from the left, I get 1. Well, those certainly aren't equal. And therefore, the derivative does not exist at 3, so it's not differentiable. So the answer is 1 and 2 only. So the answer is D. All right. So it'd be nice if you could graph this and just look to see where the function is decreasing, but this is supposed to be a non-graphing calculator question. Now, I don't want you guys to get in the habit of thinking, oh, well, if I don't have I don't care, I'm going to use my calculator when I want to. Well, it doesn't work like that on the test. On the actual AP test, they make you put your calculator with you. So make sure you guys are practicing this stuff without calculators whenever there's a new calculator icon there. So how do we do this? How can you tell where a function is decreasing? Well, g is decreasing anytime the derivative is less than 0. Or I guess another way to say that is g is decreasing anytime the derivative is negative. So let's start by finding our derivative here. So what is the derivative of g? That would be x squared plus 3x minus 70. All right, fair enough. Now, let's find where it equals 0, and after that, we can find where it's less than 0. So I'm going to plug in 0 here, and then I'm going to go ahead and factor this. Or if you want, you can use quadratic formula. I think that's a little time-consuming myself, but I end up with negative 10 and positive 7. All right, and then I'm going to do a number line test. Negative 10 here and 7 here. And I have some intervals to test now to see where that derivative is positive and where it's negative. So I'm going to plug in a number to my derivative that's less than negative 10, so like we'll say negative 11. And then we'll plug in a number between negative 10 and 7. Let's go ahead and do 0. That's always a nice one to plug in. And then 8. All right. We're going to plug those numbers into our derivative. All right, so if I plug in negative 11 to my derivative, I'm going to get 121 minus 33 minus 70. These two things put together, that's going to be negative 103. And 121 minus 103, I don't really care what the answer is. I can see it's going to be positive. So it's my f prime is positive on this interval, so it's increasing. Let's check out in between. What if I plugged 0 into my derivative? Well, if I plugged in 0, that's pretty easy because that's just going to cancel the x's out and leave you with negative 70. So that's a negative there. And it's more than likely going to be a positive over here, but we'll check it just to be sure. So let's plug in an 8. So if you plug in 8, you get 64 plus 24 minus 70. Yeah, here I'm getting 88 minus 70, and that's a positive again. So as you can see, we are decreasing anytime the derivative is negative. And I made a boo-boo here. On an FRQ, I would lose points for this. I put F, and that's not the function we're dealing with, is it? It's G. Mr. Bailey. G. Got to watch out for that. All right. So, but as you guys can see, the derivative is negative on the interval between -10 and 7. And so my answer here would be option B. All right, moving along to number 14. No calculator on this one. All right, now this is a limit question, but guys, take notice, this is not just any old limit. This is the limit of a difference quotient, which means this is really a derivative of some kind of a function. It takes that form of the standard form that we talked about. The standard form of the limit definition of a derivative looks like this. Right. So what we need to do is we need to identify, now by the way, you could do L'Hopital. Could we do L'Hopital on this? No, I don't think L'Hopital will work because there's no x's in it. So we need to identify what is our function. We need to identify at what value of x, or like I think in the notes we called it at c. And then after that, we can go ahead and find the derivative of it. And in the notes, we talked about how to handle these. You look at this first piece here. You get rid of the h, and you replace the number with an x. And that will tell you what your function is. So my function is y equals e to the negative x. And what number did we replace with an x? It was a 1. So c equals 1. So what this little mathematical representation here represents is it represents the derivative of the function e to the negative x when x equals 1. So that's the same thing as saying what is the derivative of e to the negative x when x equals 1. Okay, so that's our goal here. So once you can identify the function and what number it's at, go ahead and just find the derivative of that function and plug the number in. So what is the derivative of e to the x? Well, the derivative of e to the x is just going to be e to the x. Like it just stays exactly the same, and everything's exactly the same. But we do need to multiply it by the derivative of the exponent, which is -1. And then you're also going to go ahead and plug in the number now that they give you. So it's -1 e to the -1. Now I don't see that option anywhere, but I do know a rule about exponents that says that you can kick that to the bottom, and therefore the answer would be B. There seems to be an awful lot of questions like these in here. And like I said, these are my least favorite questions, because you actually have to kind of go through each option and see which one is true. I don't like that. But anyway, it's a calculator question, but it doesn't really matter. You can't use a calculator on any of this. You kind of just have to think your way through it. So here's what we know about this function. It's continuous. That means there's no holes or gaps or jumps. And it's on this interval from A to B. So I'm going to go ahead and draw a graph. I don't even know where A and B are. Okay, so that means it doesn't really matter where you put them, honestly. So I'll just put them here. There is a number c on the in between A and B such that f of c equals 0. Well, maybe, so if I had a graph that looks like this, like if I was going from, if f of a was down here and f of b was up there, and this is continuous, then yeah, right here in the middle it would cross the x-axis. So if I called that c, then f of c would equal 0 because it's touching the x-axis. But I didn't have to draw it like that. Couldn't I have also drawn it like this? This is also continuous on the closed interval, and now it doesn't touch the x-axis, so there is nowhere where f of c would be 0. I don't think that one has to be true. Let's take a look at another one. This one says, there is a number c on the open interval where f of a is less than f of c, which is less than b. In other words, this point is the lowest, this one's the highest, and this one's somewhere in between. Well, the way I've drawn it, it seems to be true. F of a is down here, f of b is up here, and then f of c would be somewhere in the middle. So yeah, that seems to work, right? But I didn't have to draw it like that, right? I couldn't it also be like this? All that matters is that it's continuous. So now f of a is bigger than f of b. So that doesn't have to be true either. So I've ruled this one out now. How about the next one? There is a number c in the closed interval ab such that f of c is greater than f of x for all x in a and b. Okay, now that one's a little bit tricky. But basically, what this is saying is that somewhere on the interval from a to b, notice the brackets, so that means that c could technically be a or b. Somewhere on that interval, there's a y value that's bigger than every other y value. That's the extreme value theorem. Now, the extreme value theorem says that a function has an absolute max and an absolute min. This would be an absolute max if it's bigger than everything else. So the extreme value theorem says that a function will always have an absolute max so long as it's a closed interval and it's continuous. And look, that's what we have. I've got a closed interval and it's continuous. So that means this has to be true. Somewhere there must be an absolute max. It's got to be somewhere on that interval. So I think this one has to be true. Now, just for the heck of it, though, I'm going to go through the others and show you why these don't have to be true, but we already know this is the answer. That's the one that has to be true. That's the extreme value theorem. Let's see, the next one says, there is a number c in the open interval ab such that f prime of c equals 0. Well, does that mean the slope has to equal 0 somewhere? Matter of fact, no. The way I drew it here, there is no 0 slope, so that doesn't have to be true. How about here? This should look familiar to you guys. That's the mean value theorem. The mean value theorem is only true whenever it's continuous and differentiable. But the problem didn't tell us that it's differentiable, so we can't assume this either. So by elimination, we can see that this one works also. So the answer must be the middle one. All right, move on to the next question. Let f be the function with the first derivative given by this equation here. How many relative extrema does f have on the open interval from -4 to 2? Interesting. Now, it didn't ask for relative min or relative max, just said relative extrema, so it could be min or max. So whether you're going from positive, whether the derivative goes from positive to negative or negative to positive doesn't really matter. Just so long as the derivative changes signs, we have an extrema. So anytime f prime changes signs, we have a relative extrema. Now, how can we tell where f prime changes signs? Well, one way is you could do it by hand, but notice this derivative is really, trying to find the derivative of this would be ugly. That would be really ugly. Second of all, notice the little piece of heaven over here they've given us, a calculator. I know. Why don't we graph the derivative and look at the graph to see where it crosses the x-axis? Because anytime it crosses the x-axis, it's going from positive to negative or negative to positive. So let's graph it. All right, so we have 3 minus 2x minus x squared in parentheses. And then we have sine of 2x minus 3. And let's look at the interval. We're only going from -4 to 2. So I'm going to adjust my window here. I want to go from an x value of -4 to an x value of 2. Oops. What happened? Just a second here. So I just started over there. I don't know what happened, something goofy. But let's look at it. So anytime it crosses the x-axis on the interval from -4, which is over here, to positive, or was it -4 to 2 or -2 to 4? -4 to 2. All right, so I've got my window backward. Let me adjust my window. I need to do -4 and +2. I did it again. Blasted. Sorry guys, bear with me here. So -4 and +2. Got to get that interval right. So anytime it crosses the x-axis, we have a relative extrema. Now here we can see there's clearly 1, 2, 3, 4, and here I'm not sure. Is it going just above it and coming back down? That would be 2 if it did that. So that would make 6. Or it's just bouncing off of it and only hitting it once. That would be 1. So we might want to zoom in on that a little bit and see. Let's do that. Zoom. I'm going to do ZBox. I don't use that very often, but you can do that. All right, so what you do is you move your cursor here. You push Enter. Actually, I'm going to start over because I want to go a little above that, actually. You push Enter. And then we're just going to trace out a little box around it, and we push Enter again to see. Yep, sure enough, it's hitting it twice. So we had 4 to begin with, and it's hitting it 2 more times. That's a total of 6 times it's touching that x-axis. And so the answer here would be 6. Right, so as for number 17 here, it's another one of the blue shield questions, so I can't go over this one, but good news is it's a lot like some of the other ones we've done in this little homework assignment. So we'll move on to the next one here. The mean value theorem basically is a theorem that tells you that if a function's continuous on a closed interval, which this is, and differentiable on the open interval, which it is because it's a polynomial, then there has to be some value of c such that the instantaneous rate of change at that point is equal to the average rate of change on the interval, which is given by the basic slope formula, where a and b are these numbers here, 0 and 2. So we need to find out this first of all. What is f of 2 minus f of 0 over 2 minus 0? Next, we need to find the derivative of f, which is 3x squared minus 4x. And then we're going to plug c in for the x. So let's replace these x's then with c's. Now, you don't really need to do that, but just so it looks more like what they're asking for, I'm going to put a c there. So basically, f prime of c means find the derivative, plug in c, and then the average value over here, f of b minus f of b, a over b minus a, just plug in 2 and 0 for those. So we have to find out what's f of 2. You can do that by plugging in 2 up here. So let's go ahead and do that real quick. And that's going to be 0. So this piece right here comes out to just equal 0. And how about f of 0? We're going to plug 0 in now, and that's also going to make 0. So they both come out to be 0. That's convenient. And 0 minus 0 on the top makes 0, right? And on the bottom we have 2. So basically we're left with 0 over 2, which if you simplify that fraction, you're just going to have 0. Anytime the numerator is 0, the whole thing's 0. So we have this equation, and we need to solve for c. Okay? So that's how you do the mean value theorem. Find the derivative, plug in c, do the average value with the endpoints, set them equal to each other, and solve for c. And a lot of times it will turn out to be like a quadratic kind of equation, but doesn't have to necessarily. All right, so if I wanted to solve this, I would do factoring once again. So I would factor out a c, like so, and I would set both of these equal to 0. So I would have c equals 0, and I would have 3c minus 4 equals 0. For this one, adding 4 and dividing by 3, we get 4/3. So I've got 2 answers there. Now there's 2 possible here's, but this is one where they're only asking us to find a single answer. So why are there 2 possible answers here? Did we do something wrong? Well, no, not necessarily. This is an endpoint. And when you're doing the mean value theorem, they don't include the endpoints as possibilities for the answers. The rule is that the mean value theorem applies when it's continuous on the closed interval, but differentiable on the open interval. And so our derivative, we only want to find those values of c where they exist on the open interval. In other words, we don't count the endpoints, so I'm not going to include the 0, and therefore 4/3 will be our answer. All right, for number 19, a point of inflection happens anytime your second derivative changes sign. So that's a good hint then of what we need to do. We need to find our second derivative. So let's start there. So our first derivative would be x squared plus 10x, and my second derivative would be 2x plus 10. And what I'm going to do is I'm going to set that equal to 0 to find where it equals 0, and I would end up with x equals -5. And then I'm going to do a number line test. And I'm going to test from the left and the right. And if it turns out that the left is negative and the right's positive, or vice versa, that means that it's changing signs at that point. And that would mean that -5 is a point of inflection. Now, look at your answers. It has to be this, because the only other possibility here would be well, it doesn't change signs, so there is no point of inflection, but they didn't give us that as an option. So the answer is going to be -5. But just for the heck of it, let's go ahead and check our answer anyway. So I'm going to plug in something less than -5, like -6, for instance, and then something greater than -5, like 0. If I plug 0 into this, I get 10, so that's a positive. If I plug in -6, I get -2, so that's negative. And yep, sure enough, it is changing signs at -5. So like I said, -5 will be a point of inflection. All right, let's go ahead and move on to number 20. Last one. All right, at t greater than or equal to 0, a cube has volume v and the edges of length x. Oh, that's fun. All right. You love it when they define the edges of the function also. If the volume of the cube is decreasing at a rate proportional to its surface area, which of the following differential equations could describe the rate at which the volume of the cube decreases? Okay, I think a little bit of this hinges on two things. First of all, you have to know how to find the volume and surface area of a cube. Second of all, you have to know what the word proportional means. Proportional means that, for instance, y is proportional to x if y is equal to some number times x. Okay, so for instance, like y equals 2x. That would mean y is proportional to x. All right, so you have to understand what that vocabulary means. That's a little bit tricky. We haven't done anything in here like that, but it's common math language, so whether or not you know that, I don't know, but hey, that's what the videos are for, right? Okay, so, well, we have volume, and it says that the volume of the cube is decreasing at a rate, so the volume is decreasing at a rate that's proportional to its surface area. Now, how do you find the surface area of a cube? Well, the surface area of a cube is given by the formula. You take the side lengths, which they're calling x of t, and you square it, because that's going to tell you one of the faces of your cube. You do base times height, that tells you one of the faces of your cube, and there's 6 faces on the cube. So we have that. So there's your volume, and then here's your surface area. And now, if I wanted to find dv dt, the rate of change of my volume with respect to time, that they're telling me that the rate of change in my volume with respect to time is proportional to the surface area. So it's the surface area multiplied by some number. Now, if I multiply this number by 6, I'm going to get some other number, right? So dv dt has to be equal to some number times x squared, and that would be your answer right there. And the fact that it's negative makes a little bit of sense as well, because it's negative. The slope is negative. That would mean that v is decreasing at that point, right? So that's kind of that one's a little bit off the map. Maybe not quite fair. Good thing it's not a test question, but hey, those things can pop up. But yeah, you have to understand what proportional means, and you have to know how to find the surface area of a cube. And once you know those two things, you can kind of put them together to get your final result there. But that'll do it. We'll stop there, and hopefully that was helpful, and we'll see you guys in class.